So change in the magnetic field will induce EMF alternating current generator or AC generator based on this principle. This is the labels which you have to learn for AC generator. Two things are there. In exam, the question they can ask to label the parts of alternating current generator. The second part, they can ask the working as well as sketch the output of the AC generator. So first thing, what are the labels of AC generator or alternating current generator? What we have a permanent magnet. This is a permanent magnet. Between the magnet, there is a wire, a rectangular wire, or we can also say a coil. And this coil is on the rod, which is called axle. This rod is called axle. And then this wire, the two ends of a wire are connected to the rings, which are known as the slip rings. How it works, that is the second part. The first part, you have to learn the labels. So it consists of a permanent magnet. The permanent magnet will have two magnetic poles, north and south. Between the permanent magnet, the poles of a permanent magnet, we have a rectangular coil, which is mounted on the axle. This is the axle, the rod. And the two ends of a wire are connected to the rings, which are known as slip rings. And these slip rings are connected to the part which is made up of a carbon, or we can also say graphite, which is known as carbon brush. These are the labels. But how it works, what is the function of AC generator, how it works? The simple working of AC generator is whenever we rotate the coil, as you can see, this is a coil. So whenever we rotate the coil, there will be a change in the magnetic field. And due to the change in the magnetic field, there will always be an induced EMF. So the idea, by rotating the coil between the two magnetic poles or a poles of a magnet, we can produce change in the magnetic field. And as a result of change in magnetic field, there will be an induced EMF. But how we can work out, how we can find the direction of induced EMF? To find the direction of induced EMF, we have already discussed the Fleming's right-hand rule. And according to Fleming's right-hand rule, your index finger, your first finger should point in the direction of a magnetic field. Your thumb represents the rotation of the wire or movement of the wire. And your second finger automatically represents the direction in which there will be an induced current. So example, so the right-hand rule is always used. Remember, right-hand rule is used to find the direction of a current. If we want to find the direction of a current due to change in the magnetic field. Whenever there is a change in magnetic field, we want the direction of a current. We use right-hand rule, not left-hand. Left-hand rule, there is another Fleming's left-hand rule that is used to find the force on the wire in a magnetic field. But in an AC generator, we are moving the wire. This wire will rotate, and due to the rotation of the wire, there is a change in the magnetic field. And whenever there is a change in magnetic field, there is always an induced EMF. So if I say, can you identify the direction of a current produced due to a change in a magnetic field? So what we will use Fleming's right-hand rule. So example, this is the direction of the rotation. AB is going in this way. This is the direction of the motion. And CD is going down. So we will use the Fleming's right-hand rule. According to this rule, the index finger, my index finger should point in the direction of a magnetic field. So, and I should use the right hand, my index finger should point towards the south. So in this figure, on the right-hand side is the south. So I'm finding the direction of a current in AB. So south is on my right-hand side. So my index finger is pointing towards the south. My thumb will represent the direction of the motion. As you can see in this, AB is going up, rotating. So the direction of the motion or the movement of side AB, it is up. So first finger is representing the direction of a magnetic field. The thumb is pointing in the direction of the thumb is pointing in the motion of the wire. So where my second finger is pointing, that will be the direction of the current. So what will be the direction of the current for AB? So the direction of the current will be into, or I can draw with an arrow. The black line is representing a direction of a current from A to B. So when I want to find the direction of the current for side C and D, so if we want to find the current for side C and D, so C and D, the magnetic field is south is towards the right hand side. So my index finger should point towards south. That is in the direction of the magnetic field. My thumb should represent the direction of the motion because this wire is moving downward. So my thumb should point downward. So my index finger is pointing towards the south. My thumb is pointing down and my second finger is pointing outward. So what will be the direction of the current? So the direction of the current will be outward. So this will create a current. When this wire is rotating, the current will move from A to B and then from C to D. And why there is a current? What is the reason for the current? Because there is a change in magnetic field, and change in magnetic field induces EMF. But the direction of the current will not be same. It will continuously change. So why the direction of the current is continuously changing in this? In the previous image, as you can see, AB was on the left hand side and CD is on the right hand side. But as the wire continues to rotate, so AB will be on the right hand side and CD will be on the left hand side. So first, when AB was on the left hand side, A and B were on the left hand side and CD is on the right hand side, the direction of the current was, when we work out, this was the direction of the current from A to B and then from C to D. But when it rotated, now the direction, the position of A and B and C and D is changed with reference to the poles. So as the direction of A, B and C, D is changed, now C and D is on the left hand side and A, B is on the right hand side. Again, I will apply the rule. So now first the direction of the rotation C and D in this manner and A, B and down. That's the direction of the motion of the side A, B and C, D. So again, I will apply the Fleming's right hand rule. So now for C and D, the index finger should point towards south. So my index finger is pointing towards south. My thumb is pointing in the direction of the force, direction of the motion, that is upward. So for C and D, the current is into. So for C and D, the current is going into. And for A and B, my index finger pointing towards south, my thumb should point in the direction of the motion, so that is downward. So my finger will represent the direction of the current. So current, direction of the current for A and B is in this manner. So what basically happened, you can clearly see that in the previous motion, the AB, the direction of the current was, in this image, the direction of the current for AB is up and CD is down. But the next image, when it changes the position, so when it changes the position, the direction of the current for C and D and A and B, so AB is down and CD is up or into. So when we'll see this effect on the galvanometer, or we can use an ammeter, so you can see the needle of the galvanometer will deflect right and left continuously. And why it is moving right and left? Because the direction of the current is changing. First, the current is moving from left to right and then from right to left. And at which position we'll have a maximum current or maximum voltage? When the coil is exactly horizontal there is a greater change in the magnetic field. That's why the induced EMF will be maximum. So when coil is horizontal, you can see the reading on the galvanometer or a voltmeter, or you can use ammeter, that will be maximum. But when it is vertical, it is 0. When it is horizontal, it is maximum. Then again vertical 0, and then again horizontal, so it will move in opposite direction. So this is how an alternating current generator or AC generator works. So if you start from the vertical position, it is 0, then it is horizontal maximum, and the needle will continue to vibrate. Why the needle is continue to vibrate? Because the direction of the current is continuously changing. And how we can identify the position of the coil? Like using the values. So if it is exactly 0, as you can see, if it is 0, the coil will be vertical. When I stop at the horizontal position, the voltage will be maximum. So using this idea, we can identify the location or the position of the coil, that when the coil is vertical, there is no or a very small change in the magnetic field. That's why induced EMF is minimum. When the coil is horizontal, there's a maximum change in the magnetic field, and due to maximum change in magnetic field, the induced EMF is maximum. And the direction of the induced EMF continuously changing as the position of the coil is changing with reference to the pole. So we can use this alternating current generator to produce electricity. In different power stations, we use different techniques to rotate the coil. Like example, in hydroelectric power station, we use moving water to rotate the coil. In coal, oil, or gas power station, we convert the water into steam, and steam rotate the turbine which is connected to a coil. Rotated the coil produces electricity. Same thing in a nuclear power station, a nuclear energy converted into first heat energy, which boil the water, convert into steam, and rotate the turbine produces electricity. So different power stations use different techniques to rotate the coil, but the main concept that whenever there is a rotation of the coil, there is a change in the magnetic field, and that change in magnetic field induces EMF. So due to a change in magnetic field, there is always an induced EMF. And as the coil rotates, the each side travels upward and downward, and opposite will happen due to the change in the direction of motion of the sides. There will be an induced current in opposite direction. And the direction of induced current we can work out by using Fleming's right hand rule. There are two rules of Fleming. One is a left, another one is right. The left hand rule is used to find the direction of force on the wire which is carrying a current. And the right hand rule is used to find the direction of induced current due to change in magnetic field. So here, because there is a change in magnetic field, that's why we are using a right hand rule. And this is a function of a slip rings. The slip rings are basically providing a contact so that we can draw the current out from the circuit. As you can see here, the first image. When the current is produced in the wire, how this current will flow out. So due to change in magnetic field, there is induced EMF, and the charges start to flow. And the direction of, as the direction of current reverses. So this is how the direction of the current reverses, and it produces current in opposite direction. So for AC generator, remember the rule which you will use is the Fleming's right hand rule, in which the index finger represents the magnetic field, the thumb represents the motion of the wire, and the second finger represents the direction of induced current. If we want to increase the induced current, what we can do? We can use more coils, more number of turns. Like example here in this image. Example here we have 4 turns, but we want to increase the direction. If we want to increase the amount of induced current, so what we should do? We should increase the number of turns. So 4 we can double. So if we increase the number of the turns, the amount of induced current will increase, or more induced current will be there due to a greater change in the magnetic field. And we can use a stronger magnet or rotating the coil faster. This all will affect the amount of induced current. So what will be the graph? If we sketch a graph for an AC generator for a coil, example, we start with a vertical position. Remember, when the coil is at a vertical position, there is a small change in a magnetic field. That's why the induced current is 0. When the coil rotated half, so what is this in terms of angle? How much it rotated? It rotated by 90. So when the coil rotated by 90, the induced current will be maximum. Why the induced current is maximum? Because when the coil is horizontal, there is a greater change in the magnetic field. And due to greater change in the magnetic field, there is more induced EMF. That's why when the coil is exactly horizontal, the induced EMF is maximum. So you will find a question in exam. They ask to, on the graph, label the position when the coil is horizontal and coil is vertical. So when the induced EMF is 0, the coil is vertical, so I'm using a letter V. When an induced EMF is maximum, the coil is horizontal, so I'm using a letter H. Then again it rotated further 90 degrees. So again, after rotating further 90, the total angle change is 180. And now it is vertical. So whenever the coil is vertical, what will be the induced EMF? The induced EMF will be 0. And again, the coil rotated. Again, it will be horizontal. When the coil is horizontal, the induced EMF is maximum. But what is the reason why? Here we have a positive voltage example, and this one we have a negative voltage. The reason is the rotation of the wire, the reference rotation of a wire is different. Like if I say this is a shaded part, so this shaded part initially it was moving down, and now this shaded part is moving up. So the side of the wire which is moving, that has changed. That's why the direction of induced current will be different. And when the coil is exactly vertical back again, so when it is exactly vertical, there is no change in the EMF, no change in the magnetic field, so there is no induced EMF. And this is the position vertical back again. And this one complete rotation involved 360 degrees. So one cycle, this is known as the one cycle of AC, in which we'll have a positive and the negative voltages. If I use a stronger magnet or I use more turns of a wire, so what will happen? A stronger magnet or more turns, that the amount of induced current will increase. It will produce more induced current, but the time it takes to complete the cycle will remain constant. So it will have a greater induced current, but the time to complete the vibration will be same. If we rotate the magnet or the coil faster, there will be more induced EMF and it will complete its cycle in a short time. So due to greater change in the magnetic field, so higher induced EMF, but the number of the cycles in the same duration will increase as well. Because if I'm moving it faster, in a short time, the coil can complete its rotation. So the sketch will vary depending on what change we do. If we move it faster, there will be a greater change, and in a short time, it will complete a cycle. If we only change the strength of a magnet, there will be higher induced EMF, but the time to complete one vibration will be same. Is it clear, this part? Anyone having a doubt or a question? Now some questions related to AC generator. As you can see, figure 10.1 shows a simple generator. There is a coil. As you can see, a coil is there. These are the slip rings. These are the slip rings. This one is a carbon brush, and these are the poles of a magnet. On figure 10.2 shows 10.2 sketch a graph to show how the EMF, electromotive force, or EMF induced vary with the time for one revolution. Like how the voltage will vary if it completes its one revolution. Assume that the coil start with a horizontal position. So if a coil start with a horizontal position, whenever coil is horizontal, what will be the voltage? The voltage should be maximum. And when the coil is vertical, what should be the voltage? It should be minimum. So we have to start. So basically we have to start this EMF graph with a maximum value. As I mentioned, assume that the coil start in the horizontal position as shown in figure 10.1, and label the points on the time axis where the coil has completed quarter of the cycle and 3/4 of the revolution. So example, we will always start with if it is horizontal, we'll start with a maximum. If the same question was there and the coil was started with a vertical position, so this was the position in which they give you the coil. So if this was the position, then whenever we start our graph, we'll start with a 0, minimum. But when it is horizontal, then we should start with a maximum value. So we'll start with the maximum value. The coil is here horizontal. Then what will happen? It rotate because first it is horizontal, which is maximum. Then it will become vertical. So when it becomes vertical, what will be the value? It will be minimum. So EMF will start with the maximum value and then it will be minimum. And changing from one horizontal to vertical, that is a quarter of the cycle. Like that is 1/4 of the rotation. Or we can also say 90 degrees. Then from vertical, it will change back to horizontal. So when it is horizontal, it will be maximum, but which side maximum? Because the reference position will change. So if the first horizontal, it was maximum positive, the second horizontal, the maximum will be negative. And this one, till this point, we have completed half of the rotation, or we can also say 180 degrees. Then again from horizontal position, it will be vertical position. So it will, when it is vertical position, again it will be minimum. So when it is minimum, so this will be the minimum point. And what about this rotation? So from the beginning, from the starting point, so this rotation is how much? This will be, because this was half, this was the first was quarter, then half is there, and this is 3/4 or 0.75, we can also say. And the last one, when we complete one cycle or one complete rotation, again it will be horizontal back again. So this will be maximum. And in terms of cycle, so that is one complete cycle. So this is one complete cycle according to the question. So it started with a horizontal. So from horizontal to vertical, quarter of a cycle. From vertical to another horizontal, that is also quarter, but total is half. And then to vertical, 3/4, and then this is one complete cycle. So in the question, they mention label the point on the time axis where the coil has completed 1/4 of revolution and 3/4 of revolution. So here it has completed 1/4 of the revolution, and at this point it has completed 3/4 of its revolution. Explain why EMF is induced when the coil is turning. So what is the reason for that? Remember, whenever coil is rotating, there is a change in the magnetic field. And due to that change in magnetic field, that induces EMF. So EMF only induced whenever there is a change in magnetic field. If there is no change in the magnetic field, there will be no induced EMF. State the name of a component label P and Q and state their purpose. Label P and Q. What are P and Q? For P and Q are known as the slip rings. And what is the purpose of the slip ring? It makes the circuit complete and remove the or draw the current or remove the current out from the rectangular coil, or we can say coil. So slip rings are mainly used to remove the current out from the coil. So we can use that current. State two possible changes that cause a large EMF to be induced. If you want to produce a large EMF, we should use a stronger magnet, or we should rotate faster, or we should use more turns for the coil. Out of three, any two you can mention here. If we want to induce the large EMF, so we should use stronger magnet or increase the number of turns. This is another question related to AC generator. You have a permanent magnet, north pole is up, south pole is down. These are the slip rings, and we are rotating a coil. When we rotate the coil, there is a change in magnetic field and it will induce EMF. Figure 8.1 outline an AC generator. The peak output voltage of a generator is 6 volt. Means this generator maximum it is providing us 6 volts. And it has an output frequency. Frequency means number of vibration per second, that is 10 hertz. Figure 10.2 shows the axes of voltage and a time for a generator output. On figure 8.2, mark suitable voltage values and draw the graph. So maximum is 6. So example, if we mark the 5 boxes equals to 3 and then remaining 5 boxes equals to 6, and down also 5 boxes equals to -3 and then remaining 5 boxes -6. So 5 boxes representing 3. Now we have to show that how the voltage will vary. So we should know the time period, because without knowing a time period, we cannot find how much time one cycle will take to complete its vibration. And the relation between the time period and frequency we already did in waves. So T is equals to 1 over F. That frequency and time period are reciprocal of each other. So in the question, the frequency is given 10 hertz. So what will be the time period? So it will be 1 divided by 10, which is equals to 0.1 seconds. So this will take 0.1 seconds to complete its one vibration. So we have to complete one vibration within 0.1 second. So first, if we start with a 0, like vertical position, then horizontal, that is quarter, then again vertical, that is half of the cycle, then again horizontal, that is 3/4 of the revolution, and then it will return to 0.1. So one complete rotation should be there. The time period is 0.1 seconds. So it should complete one cycle, like one crest and one trough in 0.1 second. This is one cycle. And then we want to complete the second cycle. So one crest and one trough in 0.2. This is the second cycle. Then one crest and one trough. So one crest and one trough That will be the third one. It should be according to like max, because they mentioned the maximum voltage is 6. So it should be +6 and -6. And if the question was label on the graph where the coil is vertical, so which position coil is vertical? Vertical position, the voltage is minimum. And horizontal position, the voltage is maximum. So here, if you want to label the vertical position, we'll label with letter V. And if you want to label the horizontal position, we'll label with letter H. You can mention here as well, because when it is horizontal, the induced EMF is maximum, and it is vertical, the induced EMF is 0. So generator shown in figure 8.1 works on electromagnetic induction. Explain how this effect produced magnetic field. So the whole working of generator, 3 marks are there. So you have to write these whole parts. That this will be the full answer. When coil rotate, it cuts the magnetic field lines. So EMF is induced, and that makes the current flow through a coil. And each coil rotates sideways, up and down, which changes the direction of induced current. State the energy change that occur when state energy change that occur in generator when it produce output. So what is the energy change? As you can see, we are rotating a coil. So whenever anything moving, it will have a mechanical, or I can say kinetic energy, and it produces the current. As a result, current is produced. So we call that as electrical energy. So energy transformation or energy transfer is from kinetic to electrical, or mechanical to electrical. Another question, figure 9.3 shows a rectangular coil which is placed in wire placed in the same horizontal magnetic field. The coil rotates in the direction shown, and EMF is induced. On figure 9.4, sketch a graph to show how EMF vary with the time. And on your sketch, mark with the letter T, indicate the time when the coil is horizontal. So we have to complete the 2 cycles. It's up to you. You can start with the maximum value. You can start with the minimum value. So we have to just sketch for 2 complete revolution. So this is 1 revolution, and this one is the second revolution. And the second part, on a figure, mark a letter T to indicate a time when the coil is horizontal. So when the coil is horizontal, it will have a maximum induced EMF. So I can mark, this is the time where it is horizontal, or I can mark T here as well. This is the time when it is horizontal, because when it is horizontal, the induced EMF is maximum. When it is vertical, the induced EMF is minimum. On figure 9.3, draw straight arrows to indicate the direction in which side AB of a coil is moving, and label this. So here you can see figure 9.3 shows an AC generator coil between the 2 magnetic poles. And on figure 9.3, we have to draw straight arrows to indicate the direction in which side ABs of a coil is moving, and label that as M. So we have to just draw an arrow. So which direction it is moving? It is moving up according to this. And deduce the direction of induced current and explain your reasoning. How we can deduce the direction of induced current? So we have to use the Fleming's right hand rule. So my index finger should point towards the south. The thumb represents the direction of the motion of the wire, and my second finger is pointing in. So it means the direction of induced current should be into, like, or towards the screen for side AB. So deduce the direction of the induced current. So what is the direction of induced current? That is into. And how? Explain your reasoning. So using right hand rule, or Fleming's right hand rule, we deduce the direction of the induced EMF. I'm writing in short because less than a minute left, so I want to complete that part. State 2 ways in which alternating voltage changes. Rate of AC generator rotate increases, so it will produce higher voltage. and it will be short time. The time period will decrease and the induced EMF will increase because it will rotate faster. So time to complete one cycle will be shorter and the amount of induced current will be higher.